In this video, we're going to be talking about creating tangent planes to our functions of two variables. So coming up with tangent planes that touch a surface, and then using those tangent planes to create linear approximations. So on the screen right now on the left side, I have a picture of what we're going to be doing. So we're going to be thinking about surfaces in space. That's our function of two variables. And then we'll be creating tangent planes, so planes that are just touching that surface at one point. This is analogous to in Calc 1 when you wrote equations of tangent lines. So we wrote equations of tangent lines, and we also talked about how we can use those to approximate function values. So we're doing the exact same thing, just in 3 dimensions. Then on the right side of the screen, I just have written down how we defined the equation of a plane in previous sections. So here's our equation of a plane. I'll circle it in red. This is the equation of a plane that contains the point x naught, y naught, z naught. And then I just wanted to remind you that, remember, those numbers in front of the x minus x naught, y minus y naught, z minus z naught, those coefficients on your x, y, and z actually come from your normal vector. So a vector that is orthogonal, or you could think of it as perpendicular to that plane. So this is what we're going to be doing with our surfaces in space. So we have thought of these surfaces as functions of two variables of the form z equals some function of x and y. So that's our surface. But we could also think of the surface as a function of 3 variables that's equal to a constant or equal to 0. For example, we could think of the surface f of xy. Oh, I didn't mean to go ahead. Let's go back. There we go. F of xy equals x squared plus y squared. That's a surface. That's the same thing as z equals x squared plus y squared. We could actually think of this surface as some new function of 3 variables by just moving the z to the other side to set it equal to 0. And so in this case, I mean subtracting the z from both sides. So we can think of this as the function x squared plus y squared minus z equal to 0. So we can think of it as a function of 3 variables that has been set equal to a constant. Okay, the reason I want to think about my surfaces in this new way as a function of 3 variables is it's just going to help me define my tangent plane. And so let me erase some of this because it's getting a little messy. So the equation of our tangent plane is going to be defined to be the partial derivative of our surface with respect to x times x minus x naught, partial with respect to y times change in y, partial with respect to z times change in z, where the x naught, y naught, z naught, that's the point of tangency. That's where that plane is touching the surface. And again, the f sub x, f sub y, f sub z are my partial first order derivatives. And in fact, if we were to create a vector with those partial derivatives, that vector would have to be normal to that tangent plane. Simply because earlier that's how we defined the equation of planes. The coefficients of the x, y, and z create a normal vector to that plane. All right, so now that we have our definition, let's just do an example. Let's see if we can come up with the equation of the tangent plane and the normal vector for the surface f of xy equals x squared minus 2xy plus y squared at the point 1, 2, 1. So the first thing I'm going to do is I am going to change this surface into a function of 3 variables. So I have the surface z equals x squared minus 2xy plus y squared. I'm just going to set this equal to 0 by subtracting the z. All right, so there is my function of 3 variables. And then I'm going to go ahead and find the partial derivatives with respect to x, y, and z. So I'm taking the derivative of my surface, I'll circle it, with respect to x first. So derivative of x squared gives me the 2x, and then the second term, minus 2xy, derivative with respect to x would just be minus 2y. The last 2 terms, the y squared and the z, don't have any x's, so we treat them like constants. Derivative of a constant is 0. And so there's my first partial derivative with respect to x, 2x minus 2y. And then I'll find the derivative with respect to y. So let's see, the x squared doesn't have any y's. That term goes away. The middle term, derivative is negative 2x. Y squared, the derivative is 2y. And then the z term doesn't have any y's, goes away. And then finally, my derivative with respect to z. The only term with a z in it is that last term, the negative z. Derivative of that would be negative 1. Okay, so I found my partial derivatives. And then the next thing I'm going to do is I'm going to take the point that was given, the 1, 2, 1, and I'm going to plug that into those partial derivatives. The numbers I get are going to give me my coefficients of my x, y, and z, and this will be my normal vector as well. Okay, so I'm taking the point given, plugging that into each of those partial derivatives. So first one, f sub x, I put in 1 for x, 2 for y. If there were a z, I'd put a 1 in for it. There isn't. Let's see, that becomes a negative 2. And then I do the same thing for my f sub y. Put the 1 in for x, the 2 in for y. I got a positive 2. And then finally, there's nothing to plug into the f sub z. It's just negative 1, always negative 1. So those numbers, negative 2, 2, and negative 1, actually do give me my normal vector. And I can just plug those numbers in to get my equation of the tangent plane. So the negative 2, 2, negative 1 become my coefficients. And then the point of tangency is this 1, 2, 1. And so my equation becomes negative 2 x minus 1, because that's the x value, plus 2 y minus 2, and then minus 1 z minus 1 equals 0. And so there's my equation of the tangent plane. Depending on what form the problem is asking for, we could distribute combined like terms. So this answer could also be written in a more general form as negative 2x plus 2y minus z equals 1. Again, I just distributed those numbers combined like terms. So it's just another way of writing the answer. If the directions don't specify how they want the answer, you can write it in either form. So there is my tangent plane. The other thing this problem is asking for is a normal vector. And we've actually already computed the normal vector. The normal vector would be negative 2, 2. Oh, this should be a negative 1. Copied it down wrong. There we go, negative 1. So the normal vector is just those partial derivatives evaluated at that point. All right, let's do one more. Second example, similar process. Find the tangent plane. So just like we did in the previous problem. And now we're going to also find the normal line. So that would be a line that's orthogonal or perpendicular to that plane, passing through that plane. To the surface y times natural log of xz squared equals 2 at the point E, 2, 1. All right, so first thing I'm going to do is just think of this surface as a function of 3 variables. And it's actually kind of already written as a function of 3 variables. So we can say our f of x, y, z is y natural log of xz squared. And then I did decide to minus the 2 to set it equal to 0, just to be consistent with how I wrote my other surface. Although honestly, it kind of doesn't matter because this function of 3 variables is equal to a constant. Because the 2 is a constant, it's not going to actually impact those derivatives. And so you could just say your surface or your function of 3 variables is equal to 2. Again, I'm just in the habit of always setting it equal to 0 because if the other side of the equation were not a constant, you would definitely have to move it over to the other side. Regardless, here's my function of 3 variables, y natural log xz squared minus 2. And so I'm going to have to go ahead and find my partial derivatives with respect to x, y, and z. So I started by finding my derivative with respect to x. So only x is a variable. I'm treating everything else as a constant. So that's why this y just stayed there. And then the derivative of natural log of xz squared, I get a 1 over xz squared. And then I do have to use the chain rule. I have to multiply by z squared, the derivative of the inside. Those z squareds are going to cancel out. And I'm just left with y over x. Over to the side in blue, I just wrote out another way we could think about this problem. You could use the properties of logs to expand that logarithm and then find its derivative. What I mean by that is in this, let me go back. In this particular problem, we have log of a product, and so we could rewrite that as a sum of 2 logs. And then you could even take that exponent of 2 with the z and pull it out front. So you could actually rewrite the function as y ln x plus 2y ln z minus 2. And then when you find the derivative, the only term that has an x in it is the first one. And so you would just get y times 1 over x, which is y over x. It gives you the exact same thing. So there's another way to think about that derivative. Doesn't matter how you do it. Okay, derivative with respect to y. There's only one place where there's a y, and that y is a linear term being multiplied by the ln xz squared. And so the derivative of that is just ln xz squared. And then my derivative with respect to z, looking at that first term, the y stays there. I get 1 over xz squared. And then I use the chain rule again, multiplying by the derivative of the inside. So the derivative of xz squared is 2xz. We can cancel the x's, we can cancel one of the z's, and we're left with 2y over z. So there are my partial derivatives. And then my next step is I'm going to take my point, e21, the point given, and I'm going to plug that into each one of these derivatives. So f sub x, I put in the e for x, the 2 for y, I get 2 over e. F sub y, I put in e for x, I put in 1 for z. That gives me natural log of e, which simplifies down to 1. And then finally the f sub z, I'm going to put the 2 in for y, 1 in for z, that becomes a 4. And so these numbers, my derivatives, do give me my normal vector, normal to that plane. And so those numbers are going to become my coefficients of my x, y, and z. So there's my tangent plane. I'm going to take the 2 over e times x minus e plus 1, y minus 2 plus 4, z minus 1. So I just plug those derivatives and my point of tangency in, and there's my equation of the plane. Now, those numbers, the partial derivatives, 2 over e, 1, and 4, is a vector that is normal to this tangent plane. If we're trying to come up with the normal line, that means my normal vector is the direction vector of that normal line. So again, what we're doing here is we just came up with our equation of our tangent plane, and now we're trying to come up with the equation of that normal line. So the normal line goes in the direction of that 2 over e, 1, comma 4, and it's going to pass through our point of tangency, the e2, 1. It's going to pass through our plane. And so that means the equations of our normal line, written in parametric form, would be, if we start at that point of tangency, e, 2, and 1, it would be e plus 2 over et, that's the x, and then y would be 2 plus 1t, and z would be 1 plus 4t. So I got that equations just using the pattern we learned back in, I don't remember, probably chapter 2 when we talked about writing equations of lines in space in parametric form. So again, the e2, 1 is the point that it passes through, and then 2 over e, 1, and 4 is my direction vector. So nice review of some of the things we've talked about in the past here. Now, in the past, in Calc 1, you probably learned that we can use a tangent line to come up with a linear approximation or an approximation of a function if we're close to that point of tangency. We can do the same thing with tangent planes. So we can use our tangent planes to approximate a function of 2 variables as long as we're close to that point of tangency. And so that's the next thing we're going to do. We're going to use our tangent planes to approximate functions. And so on the screen right now, I have my equation of my tangent plane written in a slightly different form, although it's the same equation we learned before. I have it written in this form just to be consistent with our book, but also to make a comparison. So when you learned about tangent lines as linear approximations, you might have seen this formula that I have circled in red, that we can approximate our function with our tangent line, which is given by the equation y equals, or f of x equals, f of a, which is our y0, plus our derivative, which was our slope, times x minus a, which was our x0 or x point. So that was our equation of our tangent line. And so there is another way we can write the equation of our tangent plane that actually looks really similar. We can think of our plane as z equals z naught plus our derivative with respect to x times x minus x naught plus our derivative with respect to y times y minus y naught. And I guess I should have put a little x naught, y naught here because we plug our points into our derivatives. So this is our equation of our tangent plane to our surface. X naught, y naught is our point of tangency. Let's take a look at some examples. And hopefully through my next example, I can show you that although this equation looks different than the one I gave you at the beginning of this video, it's actually the same equation, giving us the same information, just written in a different form. So let's look at an example of how we can create these planes and linear approximations. So the example I want to start with says, find the linear approximation of z equals x squared plus 4y squared at the point 2, 1, 8. So find the linear approximation is basically asking you to find the tangent plane. That's all it's asking you to do. And so we can find the tangent plane using the exact same method you saw in the previous examples. Or we can use the slightly different formula that I just showed you. And so let me use the different formula, show you how it's the same. So I have my surface z equals x squared plus 4y squared. Partial derivative with respect to x is just 2x. If I plug in x equal 2, I get 4. Partial derivative with respect to y would be 8y. If I plug in y equals 1, so at the point, the given, y equals 1, I get 8. And so using that formula, so again, the formula was z equals z naught plus f sub x, x minus x naught plus f sub y, y minus y naught. I get the equation of my tangent plane. So z equals, and the z value at that point is 8. So z equals 8. My f sub x was 4, and then x minus 2. F sub y was 8, and then y minus 1. So there's the equation of my tangent plane. That is also my linear approximation of this function. So I would say really the only difference between this problem, this formula, and the other formula is my equation is actually solved for z. So it's of the form z equals. Now, again, we could have used the method from earlier. And so I have that written out on the right-hand side of the screen so you can compare. And we would have gotten the exact same answer. So we could have thought of our surface as a function of 3 variables, found the derivative with respect to x, y, and z, and plugged that into the formula earlier. And if you manipulate this formula and you solve it for z, so if you take that equation and you solve it for z, you will get the exact same equation that I arrived at. So it is really the same formula, just solved for z. All right, for my next example, we're actually going to use our tangent plane to approximate the function. So this example says, use a tangent plane to approximate f of 2.96, negative 0.95 for the function x squared minus xy plus 3y squared. So the first thing I'm going to do is come up with a tangent plane at the point 3, -1. So you want to choose a point of tangency that is close to the numbers you're trying to approximate. So 2.96 is really close to 3. -0.95 is really close to -1. So the idea is to choose a point of tangency that's nice whole numbers that are easy to work with, but that are really close to the numbers given, the numbers you're trying to estimate at. Okay, so I'm going to come up with a tangent plane at x = 3, y = -1. So to do this, I'm going to find my partial derivatives of that surface. So derivative with respect to x of the surface given is 2x minus y. I plug in my point, 3, -1, and I end up getting 7. Partial derivative with respect to y is going to be -x plus 6y. I plug in my point, and that turns into -9. So there's my partial derivatives. And then my z value at x = 3, y = -1. So I'm just going to go to my function given, the surface given. I'm going to put 3 in for x, 1, I guess it's -1 in for y. I just noticed I had a little mistake there. It should have been -1 in for y. So I end up getting a z value of 15. So my z value is 15. I know my partial derivatives, and then I'm just going to plug that in to my tangent plane equation. So the equation would be z = 15 plus 7, x minus 3, minus 9, y plus 1. So there's my tangent plane. And then to finish this problem, if we want to use this tangent plane to approximate my function at 2.96, -0.95, we're just going to plug those numbers into our tangent plane equation. So I went ahead, I took 2.96, plugged that in for x. Oh, let me go back. There we go. There's my corrections. So I took the 2.96, I plugged that in for x. I took -0.95, plugged that into y, into my tangent plane. And when I did the arithmetic, I ended up getting 14.27. And so that is my linear approximation for f of 2.96, -0.95. And I could actually compare this to the exact value. If you just plug 2.96, -0.95 into the function given, into x squared minus xy plus 3y squared, I think you get about like 14.28, so relatively close to this approximation. All right, let's do a couple more examples. So if we consider our equation of that tangent plane, our linear approximation, so I have rewritten that formula in blue on the screen. Our equation z = z0, so the z value, plus some derivatives, change in x, derivative, change in y. The part that I have circled in red is known as our differential dz. It really is our change in z along this linear approximation, along this tangent plane. And just to compare with some stuff we've learned in the past, in 2 dimensions, the differential dy is defined to be your derivative, y prime, times your differential dx. And so in 3 dimensions, our differential dz, I'll circle it. Here's the formula at the top of the screen. Our differential dz is defined to be our partial with respect to x times dx plus our partial with respect to y times dy. It's actually the part of our tangent plane that I circled below. So here's an example of a problem that involves a differential. It says find dz for the function f of xy equals 2xy plus y squared. And we're going to use it to estimate delta z, which is the actual change in z, at the point 3, 2, when delta x equals 0.1, change in x equals 0.1, and change in y equals negative 0.05. So that's the first thing we're going to do. We're going to compute our differential dz, and then we're going to compare it with the exact value of delta z. So to compute our differential dz, we have to find our partial with respect to x times dx plus our partial with respect to y times dy. So looking at the function given, derivative with respect to x is just 2y. And let's see, derivative with respect to y would be 2x plus 2y. Okay, so those are my partial derivatives. So that means my differential dz is 2y times dx plus the quantity 2x plus 2y times dy. All right, finally, let's plug some numbers in. So they said we're at the point 3, 2. So x is 3, y is 2. Plug those values in. And then the delta x is going to be my dx, so that's 0.1. And the delta y is my dy, negative 0.05. So I'm going to put all those numbers in, do some arithmetic. I ended up getting negative 0.1. And so what this number is giving us, this negative 0.1, is estimating or approximating the change in z, change in height of this surface, when we change our x, when we increase our x by 0.1, and actually decrease our y by negative 0.05. So if we move from the 0.32 over 0.1 down 0.05, the height or the z value should go down by about 0.1. So that's what our dz is telling us. Delta z is the actual change in z, starting at that 0.32, and then adding 0.1 to 3, so that takes us to 3.1, and subtracting 0.05 from 2 brings us down to 1.95. So delta z is the actual change in z when we move from the 0.32 to 3.1, 1.95. And so if I want to compute my actual change in z, I'll just take the numbers 3, 2, plug it into my function. So 2 times 3 times 2 plus 2 squared, I get 16. And then I'll take the new numbers, 3.1, 1.95, plug that into my function. I used a calculator and got 15.8925. And so delta z is then the difference between, let me go back, the difference between those numbers, which is also about negative 0.1. I guess it's negative 0.1075, I think. So pretty close to our dz. All right, that was my last example. I know this was a long one. I'm glad you made it through the video. Let me know if you have any questions on this one.